All right. Part A, explain why angular momentum is conserved, and write an equation for the conservation of angular momentum between apogee and perigee. Okay, so let me draw the ellipse here. Focus there, focus there. Let's make this our sun. And let's say the comet is at this point here. That's V tangent, V there. And let us write down a truth statement here as well. Like that. All right. So this is the sun. This is the comet. The comet is orbiting the sun in an ellipse. And this is a truth statement about torque. So net torque times change in time equals moment of inertia of the orbiting object, in this case the comet, times the change in angular velocity. Now this is correspondent to its linear momentum version, which would be net force times change in time equals mass times change in velocity. Like that, right? And so if we're going to translate it from linear to angular, force would translate to torque. Time stays the same because it's just time. And then mass would translate into moment of inertia. And of course, linear velocity would translate into angular velocity. And so we can make further truth statements and say that net force times change in time equals change in linear momentum, like that, because this is just multiplication, it's commutative, so you can move the delta. And then this here equals change in angular momentum. So net torque times change in time would equal change in angular momentum. Now, between the comet and the sun, there's this distance right here. Right, that distance right there. That would be our R, let's call it our R, right? And then the force, the only force that's acting on the comet is Fg. Right, Fg is coming from the sun and is pulling the comet towards the sun. It's causing the comet to orbit in the first place. What do we know about torque? Torque equals F cross R. Right, F cross R, force that is perpendicular to the radius. Now, the only force, again, acting on this comet is Fg. And there's the distance here between them from center to center, which would be our R. Well, that distance, that line here, is our lever arm. And Fg, the only force acting on the comet here, is parallel to our lever arm. It's not perpendicular. It's not acting this way. It's acting this way. And so there's no torque acting on the comet here. And therefore, plug that back in here, there's no change in angular momentum. Angular momentum itself is still there, because obviously it's moving, but there's no change in angular momentum as it moves in an elliptical orbit around the sun. And therefore, we can make this truth statement. Angular momentum at the perigee equals angular momentum at the apogee, like that. Now, we can break this down further. Since the comet would be considered a point mass compared to the sun orbiting in an ellipse, then we can convert I into mr squared, specifically for this part, rp, right? Length of the perigee. And then we can use this relationship, v equals r omega, and solve for omega. So omega equals v over r, and plug that in for omega here. So vp over rp equals mra squared times va over ra, like that. Now, rp cancels, ra cancels, both m's cancel, and so we get this relationship. Now, this is important. For now, we're going to divide both sides by VP. So, and we will use that later. Part B. explain why mechanical energy is conserved. Write down an equation for the conservation of energy between apogee and perigee. Okay, so go back to this drawing here. Because we're in space, there is no sound and there is no air resistance. There's barely any air in space at all, and it really doesn't matter. Basically, there's no air in space. And so there will not be air resistance pushing back on the comet or anything like that. And it will not make any sound, because sound travels through air, of course. And so because of that, just like in inelastic kinetic collisions on Earth, the kinetic energy is turned into, certain types of energy like heat energy or sound energy, right? It's not all conserved throughout the system. It's turned into, sometimes it's friction, sometimes it's, again, heat or sound. In space, there's none of that. So kinetic energy has to be conserved. Again, there's no air, there's no sound, there's no really heat or anything like that that is affecting the comet. The only force that's acting is Fg, and that's a conservative force, meaning that no matter where the comet is, if it's an equal distance away, then Fg will act the same amount. Like these distances are equal, right? It doesn't matter what the path of the comet is, it only matters the distance away from the sun. And so that is the only thing that determines Fg, which is why Fg, force of gravity, would be considered a conservative force. And again, in these types of problems, there's nothing else acting on the comet, and so kinetic energy and potential energy will be conserved. And so this would be our equation. Now, the reason we subtract potential energy is that potential energy is like the debt that the comet owes to the sun, because it's bounded by the sun. That's why it's orbiting in the first place. It owes a certain amount of energy to the sun, which is why it is able to go in this kind of path. And so that's why we subtract it from the comet's kinetic energy. Of course, it has kinetic energy because it's moving. And we subtract potential energy because that's like the amount of energy that the comet owes the sun, kind of. And so that would be the statement for that. Part C, prove that tangential speed and the perigee can be expressed as turnover as Vp equals 2gms over RA, VA minus VA. Now, for this part, we are going to have to go back to our statement that we made. Rp equals RAVA over VP. And then we can also take it back to our little equation here and plug in this value for Rp. That should be a V, not an R. Dang it. Over RA. Alright, now what we can do from here is simplify this fraction. So bring the VP to the top like that. This remains put. We can multiply everything by 2 to get rid of these 1/2. So that becomes this. Okay. Now that we have this, we can cancel out all of the masses of the comet, and we can try to group all the like terms. So this. we see that there's a 2GMS over RA in both of these terms here, and so we can factor that out. P over VA minus 1, like that. And then we can turn this into a fraction with a common denominator, which would be just VA. So like that. And then this, we can turn this into a difference of squares. And now that we see there's a VP minus VA on both sides, we can go ahead and cancel that out. Like that. And then we can simply subtract VA from both sides. Like that. And so that equation there is what we are looking for up here. Part D, calculate the comet's tangential speed at the perigee and apogee. So we can take it back to this relationship that we found. And I want to find the speed of at the perigee first, and so for that we would have to solve for the speed at the apogee in terms of the speed of the perigee. So we can divide both sides by RA in this case, and then just turn the equation into that. And then we can recall our energy equation. Then we can just plug in this for VA here. Let's just go ahead and cancel out all the masses of the comet and multiply the whole equation by 2, so we can get rid of the 1/2. We can group the like terms together. Here we can factor out a VP squared because we're going to be distributing the square, and here we can factor out a 2GMS. We can distribute this square and find a common denominator for these two fractions. And then from here we can also find a common denominator for these. RA squared. Rewrite this. And then we can turn this into a difference of squares. We have RA minus RP on both sides, so we can cancel that out. We can multiply this term by the reciprocal of this fraction here, so we can get VP squared by itself. This was the equation. Just got another paper for the next part. And from here, we can cancel out one RA. And so VP equals the square root of 2GMSRA over RA plus RP times RP here. And then we can plug in those values, plug all of that into our calculator, and we get VP equals 69,504.345 meters per second. And then we can just use this equation here that we found earlier. So VA equals RP VP over RA. Plug those values in. And we get 5,811.019 meters per second. Part E, prove that the general formula of the comet's tangential speed around elliptical orbit is V equals the square root of GMS times 2R over 1 minus A. Okay, so what we know is that total energy in orbit, like any orbital system in space, equals negative GMS. Well, in this case it would be the sun, but this M is usually just the stationary celestial object. This M is the orbiting celestial object. Over 2R, R is the distance between the two objects from center to center. And that is the equation for total energy, because the orbiting mass owes energy to the stationary mass. That's why it's orbiting in the first place. It has an energy debt, right? Now, Kepler's third law is actually applicable for elliptical orbits as long as you use the semi-major axis A for R here. And so we can say that that is equal to GMSM over 2A, negative GMSM over 2A, like that. And so we can simply write out our equation minus GMSM over R, or I guess, yeah, R, because we're not specifying if it's the perigee or apogee yet, equals negative GMSM over 2A, like so. We can cancel out all of those. And so what we have here is 1v squared, 1/2 v squared, and then GMS over R, negative GMS over 2a. Now, we can add this to both sides, so GMS over R minus GMS over 2a. What we can do is multiply everything by 2 to get rid of that 1/2. GMS over R, and then the 2's here will cancel out, so it's just GMS over A, like so. And then we can square root both sides, so it becomes S over R minus GS over A. And then we can simply factor out the GMS here. So S equals 2 over R minus 1 over A. And that is what we were looking for up here. Now, part F. If the comet were in a circular orbit of radius R orbital equals RP at the perigee, is its velocity v orb greater than or equal to or less than the velocity v of the perigee of the original elliptical orbit? Okay, so what we know is that v orbital in a circular orbit equals square root GMS for the sun, or we can just say, stationary object here, over the radius, whatever the radius is. And for elliptical, well, we have our equation right here. Now, in this case, our R, like here, would be RP, right? And so VO in this case would be GMS over RP. And here we can turn that into RP as well. So VP in elliptical equals GMS times 2 for RP minus 1 over A, like that. Now, if we go ahead and draw the ellipse again, just for visual aid here, see, the geographical center of the ellipse would be over here, and then A would be this distance. Now, if there's a focus here and a focus here, then this distance right here would be the perigee. And then the rest of the distance would be the apogee, but we're not going to label that A because we already labeled the semi-major axis A. Now this will help because this has 2 over RP and this technically has 1 over RP. Now, of course, 2 divided by the same number will be bigger than 1 divided by the same number. And so we know that this is bigger than what is being multiplied here in this square root here. Now, obviously, A is bigger than the distance of the perigee because the perigee is the shortest distance from one focus to the edge of the ellipse, while A is the semi-major axis. It's half of the whole distance of the ellipse from edge to edge. And so A is greater than P. Now, because of that, 1 over A will be less than 1 over P, because 1 divided by a bigger number is obviously going to be smaller than 1 divided by a smaller number. And so, because we are subtracting this from this in this equation over here, and this is bigger than RP here, right, then that means that 2 over RP minus 1 over A has to be greater than 1 over RP, because this is obviously bigger than this, but this is less than this. And so if you subtract something that is less than this from this, then the result will of course be greater than this, because this is smaller than this. And since this is in this square root and this is in that square root, then a bigger number is in this square root being multiplied by GMS, while a smaller number is being multiplied in this square root. And so this square root will end up being greater than this square root, and therefore we can conclude that VP in an elliptical orbit will be greater than V orbital when you're using the distance of the perigee for your circular radius.